So before I dive into explaining what MLbase actually is, I want to give you a really brief background, like how this project actually came together, because like it was quite a shift from what I was doing before. I have a database background. I worked mainly on transaction processing and recently also crowdsourcing, and this was a new thing. And of course, there's like the motivation that big data is very hot, and we had like already a couple of talks about like how big the data nowadays is from Facebook, and I think they are like in science the really extreme examples like the LHC, the collider, which is really producing a lot of data, and so there's a lot of data around, and you actually need to make sense out of it. And normally, if I talk to like colleagues and so on, this is the official explanation I'm giving them. But that's not the whole reason why I started with my colleagues at Berkeley this project called MLbase. There's a strong hidden motivation I have, and it's motivated by a PhD comic I saw a couple of years back. And this comic simply doesn't leave me alone since I joined Brown as a new faculty member. It is about the hair migration pattern of male professors. And what you see there is like during like grad school, you have a brief flirtation with facial hair and like the beard essentially. Then 5 years before tenure, it's like slowly migrating from your top down, and you're growing a beard and you're losing all your head hair actually. So I did a really, really small study. I looked at my colleagues at Brown, like the colleagues I have in the database group, and that's them. So it's a very bad sign already, right? So I looked then at the other colleague, and that's Ur, actually just when he started the tenure track at Brown, and that's Ur now. So I'm really, really worried, right? And I thought, okay, it shouldn't be so hard actually to verify if this is true or not. If there's a strong correlation between like how your facial hair over time essentially migrates if you become a faculty member compared to the rest of the population. Because there are like so many pictures out there, right? Like Facebook, Flickr, and so on. It's all accessible. The only thing you need to know is just like to connect it to people, look at over time, figure out the main describing features. And so I really wanted to do that, but it turned out to be very, very hard, right? So, and this is a general problem if you really want to use the different like algorithms which are out there in order to make like sense out of data or big data or pictures or whatever it is. So let's assume even like a simpler task, like let's say we want to build a simple classifier over some data set. So actually the specification is very simple. I want a classifier. But then there's all this crap I have to do, and like I have to know about modern classification algorithms. I need to know how to balance them. I need to implement some infrastructure in order to try several of them. I need to figure out what are the right features, and so on. There's like this whole machinery machine learning people actually do over and over again, right? And in the end, if you're not really in this field, what you end up with is like you ask for help, right? You actually go to somebody who actually knows better what's going on. And this problem that there's so much things you have to do over and over again, that's the motivation behind MLbase. So MLbase tries to make it a little bit simpler to use all the inference algorithms and like analytical algorithms in general, which are out there. So the first goal of MLbase is really to simplify the use of machine learning algorithms. And then we have some other goals to it. One of them is also we want to make it a little bit easier to implement distributed algorithms. And my take on it is really like from a systems perspective. However, if you're switching fields, the first thing you are doing, of course, is you get together with like great people who actually know this area much better than I do. And in particular, I want to mention like Amit Talwalker here on the left, who just happened to be, when this project started in the MLab here at Berkeley, we just got along and we started this thing together. And then soon after, we got like a great PhD student, Evan Spark, here on the right, who is now one of the driving forces behind this whole project. And since then, many other people joined and are bringing this thing forward. So what is the goal? The goal of MLbase is to do something very similar what databases actually did for data management. It tries to provide a declarative approach, allowing the user to say what he wants instead of how he actually achieves it. Right? So in databases did it for a long, long time. They have a SQL interface, which is a declarative language. You specify your result set essentially, and the system figures out how to evaluate it. And the system figures out what indexes to use, what data structures in between, how to store the intermediate results if it doesn't fit into memory, and so on. And we would like to do something very, very similar for machine learning. The user specifies, like in a declarative way, at the moment we call it MQL, the machine learning query language, what he wants, and the system somehow magically figures out how to achieve it and gives the result back. Of course, this system cannot achieve the same quality or performance as a highly tuned, like, individual solution. Right? If you have an expert and he knows really the area perfectly, he will always come up with a better way to solve it, to make it faster, and so on. But that's also not our goal, and actually it's also not like any different from a normal database system. A database system gives you a reasonable performance for most cases. But the C++ implementation, highly tuned for a certain application, will always beat it. Right? And that's also similar here. We just want to get the same spirit, to give you a reasonable implementation, which plus is also like easily be deployed in a production system. Right? And normally if you look at the typical workflow, people play around first with R, they try to figure something out, maybe at some point they come up with something which actually really works, and then they go to the systems people and just say, please implement that in production. Right? Which is just another big burden, and hopefully we can also simplify this process a little bit. So in order to drive the development of MLbase, we have a bunch of use cases, and we developed this higher language. This was here just some code examples from our first draft, and it's still changing. That's definitely not the final version. And it should just give you a feel how it might look like. Right? It's definitely not the final version yet. The important thing, for example, to do a classification, you load the features, you load the labels, which are the first two statements. Then you say you want a classifier. And then you say you also give it a time limit until you want to have at least one result back. And I come to that in a second, why you need this top 5-minute thing. So without going into more detail here how this language looks like, the important takeaway is that we try to provide something which we call algorithm independence. Again, you say what you want and not how to achieve it. You don't say only use this particular algorithm with this particular configuration setting. Right? Instead, you just say you want a classifier, and the system should figure out the rest. So you are always asked, but if I know better? And sometimes you do, you know better. But then we take again a similar approach what databases also do. The developer can provide hints and therefore steer this whole process in a certain direction. Right? So that's your way to influence it. But still, you can take advantage of all the built-in mechanisms in the system. So how does this whole data model work? So normally databases have something like a relational model behind it, which is the foundation, how it works. This system is a little bit different because in the end what we want to get back is a model. And we designed a new data model which consists of a stream of models or tuples which can pass around so everything is composable. But if you call, for example, the do classifier, which gives you models back, what you're getting back is actually a stream of different models. And you just have to pick the best one you like. Right? So you get the system is continuously actually developing or creating new models out. And you just have to say, now it's good enough. Now I have enough quality. I'm satisfied. I stop looking at that. So that's the reason why there's this top statement in there. The stop means, for example, after 5 minutes, just simply takes the best. So looking at the whole infrastructure, this is the initial design of the system. It's pretty much designed along the lines of a distributed database system. But there are some key differences. First of all, we are targeting from the beginning a distributed runtime. But this is in the beginning, at least, it wasn't our main focus here. We just said hopefully we can build on top of other runtimes like Spark, even Hadoop. But we want to abstract away from it so that you can, whatever platform you have in-house, you can simply use it. And how we do it, we provide something what we call MLeye, which is just an abstraction so that you can use other platforms underneath. And I'll tell you in a second a bit more about that. The next thing is we wanted this whole system to be very extendable. So machine learning developers should come along, create a new algorithm, plug it into the system, and should be taken advantage of by the whole infrastructure and optimizer. Right? So because the field is always evolving, people are coming up with new ideas, so we want to leverage them. And this is also a key difference to other systems, because normally what you do is you develop an algorithm in R, and if you are really friendly, you put it out on the web for other people to use. But there's no really common standard on how to integrate them and how to trade them off, and it always requires a lot of time to compare them, actually. And last but not least, we want to have this optimizer approach, so that the system really figures out what's going on, and therefore we need statistics about the data as well as the algorithms, and I will also tell you more about that, as well as an optimization approach to it. So let me start off with the lowest level, the MLeye, the abstraction. So the MLeye layer is a really simple abstraction over different runtimes. It's supposed to provide what database people call physical independence, meaning that only on a high level you specify how something should operate, but then you deploy it actually on a specific infrastructure. So we have some initial abstractions like MLtable, MLmatrix, and MLopt. And there are two runtimes right now which implement them. One is Spark and another one is Tupperware, a system we're currently developing at Brown. That's all I want to talk about these abstractions. If you want to know more details, Amit is sitting somewhere in the audience over there. So the second component is the Bynars of algorithms. And so MLeye essentially provides a really simple abstraction so that machine learning developers can implement a distributed new machine learning algorithm without worrying too much about the internals, how it actually is executed. So the Bynars now make it accessible for the system. And the Bynars consist of two parts. One is the implementation, which is done hopefully on top of MLeye, but you don't have to. You could even use other languages like R and completely ignore the rest of it. But then the system could also not really optimize them. So it's a trade-off you have to make. And in addition, what you need to provide is a contract. And the contract is actually telling the system what this algorithm does. Right? It tells you the parameter space it should consider, the runtime which you could derive, but at the moment you have to specify it, and some high-level statistics essentially an optimizer can take into account. What we have today is just like what I would call half full of binders with some really common algorithms. And they're all released as part of Spark. So just to give you a really brief feeling how it looks like, we compared for alternatingly square the implementations from MATLAB, MLeye, Graphic, and MLeye. What you see is MLeye is actually pretty close to MATLAB. And performance-wise, this is just like for scaling with different numbers of machines, the total time it takes. You can also see that it's in the same ballpark as, for example, GraphLab, and of course performs better than MLeye, which is not really surprising given how the infrastructure works. So the total numbers here are not really important. It's just like to give you a feel that we are not much worse if you follow certain rules and how to implement the algorithm. Okay, so moving on to the next step, the optimization. The optimization. So there are two things you need to consider there. It's like, first of all, the statistics about the data as well as the algorithms, and then there should be some feedback loop. So let me give you a brief idea how that works. So taking a general specification here on the left, which just says, okay, load some data, var x as like the features, load some data as the labels in y, and then please generate a classifier out of it from x and y in 10 minutes and return back the best model, which is the top. So some of these constructs here can be directly translated what database people call a logical plan, which is a general specification about the workflow. Right? It doesn't say concretely what algorithm to use or how to do it. It just says you have to do a certain operation. For example, load the data. Some of them are these operations like the load is directly translated into the logical plan here. Whereas what we do in addition is that some other operations, like the doClassify, for example, are expanded to what we call best practice workflows. Right? They incorporate like the typical step a developer might take. Right? For example, it searches over different algorithms, it tunes or it like tries out different normalization factors. Important in particular is also like certain validation steps. Right, like the typical things you would normally do if you try out a new data set. Right? And so we just wanted to incorporate like as much as possible of them in this workflow automatically for you. Of course, important is in the moment you get then the final result back here, what you're getting back after, let's say, 10 minutes in this case, is one, the summary, one, the model, like the best model we found, but also the summary, which explains the process, what the system was doing to find this model and what it tried out. So in the end, this summary provides you whole lineage information. And it's very important that you look at this lineage, what was actually going on in the background for you. So after we have this logical plan, now the second step happens, which is actually optimizing this plan, what databases people refer to as a physical plan, which is then really saying, try the following things out on the physical hardware in the following way with the following scheduling and the following techniques and so on. So it's like really taking this like general specification and translates it to something it actually can execute. And in the traditional world, the optimizer has actually a very, very simple goal. It's time. Right? The traditional optimizer for a traditional database system, if it looks at the query, it just optimizes it for time and tries to figure out the best plan to give the answer back in the shortest amount of time. In MLbase, it's a little bit more complicated because in the end, we have two optimization goals. One is quality, and the other one is actually the time. Right? So waiting forever for an answer doesn't help you, even if it would be the perfect answer. But at the same time, if you give an answer back really quickly, and in a classification case, it just might be that you say everything falls in category A, which is a very simple classifier, right? You could do it immediately, and it also doesn't help you. So you need to trade the both of them somehow off. And the trick, what we are doing, is we say one of them normally has a budget. Typically, we give it to the time. We say after 10 minutes, at least give us one model back. But in addition, what we also assume is like even after 10 minutes, the system simply should continue running and produce further models. Another difference is that what we want to do here is consider the different algorithms and systems techniques at the same time. So we really want to leverage both worlds. And there's a lot you can do, and I have some examples later on. We need to collect statistics about the data, which databases normally do, but also about the algorithms themselves. Right. And we want to do this like all across the steps, which like normally if you have a query optimizer, it's just like it's one query plan. Whereas like here we are more in the world of like workflows. So that also changes quite a bit like how you have to do the optimization. The last very important point is this whole thing has to be robust. Whereas like in the normal traditional database case, if you screw up the optimization phase, it doesn't matter so much. The only consequence is like your query is running slower. If you screw it up here and you make the wrong decisions, right, your quality might degrade by quite a bit. Right? Hopefully we are always better than like normal naive grid search techniques, but still it's something you have to consider if you search the space too aggressively. So there are a whole bunch of possible optimizations out there, ranging from like static selection rules, because you know that certain things are better than others. Runtime optimizations, so in the moment you start the whole thing, you can exploit like certain caching strategies and use the feedback you're getting during the like running a certain algorithm. And they're like the most interesting one I believe is just like the cost-based optimizations. I just had like a talk with Chris Ray. He mentioned like really unique possibilities, for example, to use materialization and indexes to speed up certain algorithms. And that's another really great opportunity here. So let me give you some really like simple cases just to give you a feeling about what an optimizer might be able to do. The one thing is, it's very simple, but often forgotten, is just to check for imbalance of labels. Right? You run a classifier, you have an imbalance of labels, just saying that like one of the populations is just overrepresented compared to the other one. Is like here the case in the one down here, the red ones are way higher than the blue ones. Right? If you now have a very simple classifier, in this case below here, and you just say everything should be classified as red, actually your precision is quite high, but it's just an imbalance of labels because one population is so overrepresented. It's very, very simple to fall into this trap if you don't look into your data more carefully. Right? So this is something a system could easily figure out just based on histograms of the data, and that's something databases already stored today. It's not even something new we are inventing here. We just have to leverage it in the right way. Another reason why to optimize, of course, is quality. And we just ran a really, really simple experiment here with some publicly available data sets using SVM and AdaBoost, ones with like a scaled feature set, one on the original ones. And what you see here is just like the green ones are always the best accuracy rate, and you see there's not a clear winner here. So algorithms perform differently. And this is really like a naive example here, but it should just give you a feeling that there is optimization potential. In the same regard, we ran an experiment for SVM and AdaBoost and just varied the parameters. In one case, the scale factor, and for AdaBoost, the regularization a little bit on the same data set. And what you see here is like in SVM, the performance, the accuracy of the algorithm actually heavily depends on the scale factor. So it has like a huge impact on the accuracy. Whereas like for AdaBoost, the regularization factor, at least for the values we chose, didn't have like a huge impact per data set. And this is one data set always, right? So like the lines, you see them if they are closer to each other, the impact is not as big, at least for the data we chose. So this gives you already some hint on how an optimizer might work. Is, for example, you can say, okay, let's try AdaBoost first because it's more robust, and then move on, for example, to SVMs, which more heavily depends on the different parameters, right? And you have to search longer until you find something good, but that might be then better than the rest before you go back and tweaking the parameters here for AdaBoost. So another reason why to optimize is systems performance. So if you run a single algorithm at a time, often you tend to be I/O bound. So there's a very simple trick in the database community called shared cursors, which is just saying, okay, let's do a couple of things together. Right? In this case, we could run a couple of like trainings at the same time and just like do it in one pass over the data as long as this fits into the cache and so on. So the question then comes down to like how many models at the same time we should actually train. What is the impact, for example, on sampling? Like, can we downsample the data in order to fit in more models, or when does it actually break? And in the same regard, it's like how to leverage the modern CPUs, in particular vectorization, because that influences how much we are actually I/O bound. So this is again a very simple experiment we did for one of the core loops of one of the machine learning algorithms. And again, it's just like to give you a feeling how this speed up might look like if you do the right thing. So here is like on the x-axis the numbers of data elements. On the y is the speed up compared to a linear version. And what we are showing here is like vectorized over linear. And what you see is just like if you are able to squeeze in more data into your cache lines, you get actually huge speed ups. But if you are too small at some point, it degrades again. And that's a really funny effect modern CPUs actually have. Right? So as long as you somehow utilize your cache lines, you can get like huge performance speed ups. And I just want to note here that we are comparing actually to ourselves and not Hadoop, right? So therefore you don't see like a 10,000th of speed up in this graph here. Like if we would compare ourselves to Hadoop, the numbers would even look way better. And it's like just a very low bar in general. So the direction, so currently what we have, we released the MLeye interface as well as a half full of Bynars as part of Spark. We have some very simple feature extractors and some end-to-end use cases. But we are heavily working on, in particular, on the optimizer part. We are trying to develop new techniques, how we can leverage like both worlds, the system world as well as the knowledge how like machine learning algorithms have to access the data and how to speed that up. We are looking into the cost-based optimizer, the language approach, as well as like implementing more advanced machine learning techniques. So to summarize, MLbase is the first declarative machine learning system, which provides you a declarative approach so that you can say what you want and not how to get it, and the system somehow magically figures it out. And its goal is to simplify machine learning in the same way as databases simplify data management. And as a small teaser, there's this like new system, Tuppleware, we are working on, which again is supposed to make machine learning implementations faster and easier to do. So with that, thank you, and I'm open for questions.